Good morning. So yesterday evening, I have introduced the concept of optical solitons. So now we will talk about the process of modulational instability, which is strongly related to the process of solitons, and in particular to bright solitons. So if you consider the interaction between nonlinearity and dispersion in any systems, like an optical fiber, so continuous wave or a long pulse can undergo modulation of its amplitude or phase in the presence of noise or any external perturbation. So it's a very general process. Here, instead of an optical fiber, you can have a mechanical system, an hydrodynamical channel, or biological system. So it's very general systems. So the perturbation can come from the spontaneous emission, in the case in optics, or it can come from an external signal. So we can induce the process, or the process can be spontaneous. So if you look in the frequency domain, you have here the generation of sidebands, which are related to the self-modulations of the intensity of the waves. So in the case where you induce the modulational instability, you will see that this process can be used to generate a pulse of generate train of pulses, train of solitons with very high repetition rates. So it's very useful in practice also to generate, for example, frequency combs. So to understand this process, we will use the linear stability analysis. So in that case, here we will consider the scalar modulational instability. So again, I will assume that the state of polarization is maintained during propagation. It's, again, to simplify the things. So, and we will see that modulational instability in optical systems can appear in the case of anomalous dispersion regime. So we start from the nonlinear Schrödinger equations, and we will examine the linear stability analysis of its steady-state solutions. So first, we look for the stationary solutions of these equations, and then we will perturb these stationary solutions. So to obtain the stationary solutions is very simple. You have just to remove here the time term, so that's equivalent to remove the dispersion terms. So you will find solutions which are similar to the solutions that we have for phase modulations. We have a term which is proportional to the square root of P0 times a phase term with a nonlinear phase, which is proportional to gamma P0 and psi the distance of propagation. So now we have the stationary solutions. So we add to this stationary solution a perturbation, a small perturbation, so a small function A, which will depend on the propagation distance and on time, of course. And we assume that A is a complex function, just to take into account phase and amplitude perturbations. So if we do that, we inject this solution into the NLS equations, and then we remove the terms which are not linear with respect to the amplitude A of the perturbation. So this approximation is called the linear stability analysis. So if you do that, finally we obtain an equation which is very similar to the NLS equations. Here in the right part, you have the sum of A plus complex conjugate of A. So now to solve this equation, to find the condition of modulational instability, we have to make an ansatz. So we assume that the perturbation can be written like that. It's a sum of a cosine function and a sine function with k and omega here, the wave number, on the perturbation, on the frequency of the perturbations. So, but we can expand also this function as a function of exponential terms, and you can see that A is the sum of two exponential terms with a propagation term here of the perturbation. So this ansatz is simply a Fourier decomposition of the perturbation. So if we do that and you inject this solution into this equation, so you will find the conditions for the perturbation to develop. So we find the dispersion relation for the perturbation. This is the relation between k and omega. And we can see that modulational instability will manifest itself by an exponential growth of its amplitude. So here in this equation, you can see if k is has an imaginary part, so you always have an exponential amplifications of one of the two terms, if k has an imaginary part. So that means if k squared is negative. So we have to look at what condition k squared is negative. So that means in that case, the perturbation will amplify exponentially. So, and we will see that will depend on the sign of dispersion. If beta 2 is positive, so gamma is positive. If beta 2 is positive, so k squared is always positive, and k is always real, whatever the value of omega. So in that case, the steady-state solution is stable. So we cannot have modulational instability. But in the anomalous dispersion regime, this term is negative. So we can have k squared negative. And it happens when omega, the frequency of the perturbation, is smaller than a cutoff frequency, omega c, which is defined by omega c squared equal to 4 gamma p0 over absolute value of beta 2. So it depends on the fiber parameters, gamma and beta 2, and it's proportional to the initial power, p0. So from the previous equation, you can see that in that case, if you replace k by imaginary part of k, you have an amplification of the power of the perturbation, which is proportional to exponential of 2 imaginary part of k times psi. So we can define a power gain for this modulational instability, which is a function g of omega, which is equal to 2 times the imaginary part of k. So it's simple to find this function, the growth rate of the instability. So we get this term, and it's very simple to check that we have a maximum of this gain, so which happen for this particular optimal modulational frequency, which is equal to the square root of 2 gamma p0 over absolute value of beta 2. And the peak value of the gain, G max, is equal to 2 gamma p0. So therefore, we can see that modulational instability it does not depend on dispersion, but increase linearly with the incident peak power and with nonlinearity. You can see that from the expression of the peak of the gain. So here, this is the spectral profiles of the MI gains that we can obtain for different values of the input power, 1 watt, 3 watt, 10 watts. And we can see that optimal frequency and the peak gain increase with the input power as it should be. And here, so what very interesting things, if you look at the frequency value here, so you find that the frequency of modulational instability is a few hundreds of gigahertz or even a few terahertz. So that means that it's possible to make frequency conversions over a wide spectral range. And here, this is an experimental spectrum obtained with neodymium laser. And you can see here the power is 3 watt, and the fiber length is 1 kilometer. And you can see the generation of modulational instability side bands. In that case, it's a spontaneous modulational instability. And the optimum modulational instability frequency is close to 300 gigahertz, which correspond to the value that we have here for the MI gain for the power of 3 watts. So it's in good agreement with the prediction of the linear stability analysis. So now what's most interesting is to induce the modulational instability process. So in that case, we inject into the fiber a second wave, which we call the signal wave, with a smaller amplitude, and with a frequency detuning with respect to the pump, omega, which is between 0 and the cutoff frequency omega c. So if you do that, and for a particular value of the power, so you induce, at the beginning of the propagation, you induce a small modulation on a continuous background. And you can see that these small perturbation oscillations increase as a function of the propagation distance. And at a certain distance, we have the generation of a train of pulses. And if we look in details at the shape of this pulse, of each pulse, we can see that it corresponds to a solitons. It has an hyperbolic secant shape. So we have generated here a train of solitons at a very high repetition rate, about here 340 gigahertz. But for other fibers, for other initial power, it's also possible to obtain pulse repetition rates up to a few terahertz. So if you look in the frequency domain, we have a frequency comb here, whose shape is given by the Fourier transform of one single pulse, and the frequency separation between two frequency combs correspond to the frequency detuning between the signal and the pump. So it's a very interesting solution to generate a frequency comb, to generate a train of solitons at high repetition rates, a few hundred of gigahertz or even a few terahertz. So this process of modulational instability can be also interpreted in terms of four-wave mixing. It's a four-wave mixing process in which you have two pump photons which interplay to generate a Stokes photon and anti-Stokes photons. So in that case, the two pump photons have the same frequency, so it corresponds to a generate four-wave mixing process. And these the two sidebands, the Stokes and anti-Stokes sidebands, are located symmetrically with respect to the pump and with the frequency detuning omega, which can be obtained from the phase matching conditions. So here, if you write the conservation of energy, you have omega p plus omega p equal to omega p plus omega. This is the frequency of the anti-Stokes sideband. And plus omega p minus omega, this is the frequency of the Stokes sidebands. So this conservation of energy means that the two sidebands are located symmetrically with respect to the pump. Now, if you write the phase matching conditions, so it will give 2 beta at the frequency omega p equal beta at the frequency omega p plus omega, plus beta at the frequency omega p minus omega. But omega, if it's of the order of a few hundred gigahertz or a few terahertz, so it's smaller, much more smaller than the frequency of the carrier waves. So we can perform a Taylor expansion of beta at the frequency omega p plus minus omega around the frequency omega p. If you do that, don't forget the nonlinear term due to the Kerr effect, and we obtain the very simple phase matching conditions, beta 2 omega square plus 2 gamma p0 equals 0. And you can see again, this term is positive, so the phase matching conditions is satisfied only if beta 2 is negative. So we check again that modulational instability happens only in anomalous dispersion regime. And we obtain the optimal modulation frequency just by solving this equation, and we obtain omega opt equal plus minus the square root of 2 gamma p0 over the absolute value of beta 2. It's exactly the value that we have obtained from the linear stability analysis. So this four-wave mixing interpretation is very simple to have a very quick idea of the optimal modulation frequency. But it does not give the gain and so on. So maybe I can do a remark at this point. So modulational instability is more general than parametric amplification. Parametric amplification is a special case of modulational instability. We talk about modulational instability each time that the nonlinearity is necessary to have the phase matching conditions. But for parametric amplification, for example, you can have phase matching between dispersion and birefringence, and you don't need the nonlinear contribution. So we will talk about modulational instability each time that the nonlinearity is essential, crucial for the phase matching. So it's a more general process. And in the textbooks, it's something which is a little bit confused. So before going on, I would like to say that this modulational instability process is a particular case where we are concerned only by one mode, one polarization state. Of course, if you take into account the two polarization states, which can happen in a birefringent fiber, or the two spatial modes in a bimodal fiber, so you can have an extension of the process of modulational instability. In that case, we talk about vector modulational instability, and in that case, we can have a modulational instability even for normal dispersion. And it's the same for solitons if you take into account the state of polarizations. So you don't have a single nonlinear Schrödinger equation. You will have two coupled nonlinear Schrödinger equations. And these two coupled nonlinear Schrödinger equations will lead to the generation of vector solitons. So vector solitons are solitons which have two polarization components, and each polarization component will shift their frequency during propagations in order to propagate at the same group velocity. So that's the idea of the vector solitons. So now I will talk about scattering phenomena, and in particular about Raman scattering phenomena. So it's not the topic of this lecture, but it's necessary to understand a few phenomena which can happen in the propagation, during the propagation of a pulse in an optical fiber. So as you know, the parametric effect is corresponds to an energy exchange between waves, but there is no energy exchange between waves and matter. Okay? But for scattering phenomena, like the Raman scattering or Brillouin scattering, you have an energy exchange between the wave and the matter. And this energy exchange so induce a modification of the energy levels of the molecules, and this corresponds to an interaction with an acoustic waves with the phonon. And we can understand the process of Raman scattering or Brillouin scattering just by looking at the dispersion curve for dielectric materials, which is simplified here in the case of a crystal, just to see the theme more simply. And the acoustic branch of the dispersion curves will lead to the Brillouin effect, and the optical branch of the dispersion curves will correspond to the Raman scattering phenomena. But both Brillouin and Raman effects are very similar. Okay. You have interaction between photon and phonons. So in the case of the Raman effect, for example, here, if you consider a molecule which is in the ground state, this molecule can absorb a part of the energy of the incoming photon, and the molecules will go into an upper levels, and simultaneously you will have a radiation of a photon at the Stokes frequency omega s, so at a smaller frequency. And on the other hand, if the molecule is in the excited state, so when it absorbs a photon of the initial waves, so the molecule turn back into the ground states, and simultaneously we have a radiation of an anti-Stokes Raman photon. So both processes are similar. We have a Stokes and anti-Stokes radiations. So in the case of silica, the frequency shift here between the two energy levels is about 13 terahertz. So that means that at room temperature, the number of molecules in the excited states is relatively small with respect to the number of molecules in the ground states. So that means the Stokes process will be more intense than the anti-Stokes process. So it's difficult in optical fibers, for example, to observe the anti-Stokes Raman radiations. They have very small intensities. This is due to this frequency shift, which is 13 terahertz. If you observe Raman effect in a gas, for example, so in that case, you can have a very small energy shift, and you can observe, of course, anti-Stokes and Stokes Raman radiation. So what is important is that if the power of the incident waves is relatively small, so the process will be spontaneous, and we talk about spontaneous Raman radiation or scattering. And if the power of the initial beam increases, so in that case, the process can be self-stimulated, and we talk about self-stimulated Raman effect. So, and this process corresponds to the fact that the energy is continually converted from higher to lower frequencies. So, as a result, the amount of Stokes photons is continually amplified at the expense of the anti-Stokes photon. So that's also a second reason why it's difficult to observe the anti-Stokes Raman line. We have always an energy transfer from the anti-Stokes frequencies to the Stokes frequencies, thanks to this Raman effect. So to go in more details, so we will look to the case of stimulated Raman scattering. So we can explain this effect by looking at the nonlinear polarizations. And we can here in this to interpret the phenomena in terms of nonlinear polarization, we have to add to the Kerr effect, we have to add this Raman effect, which is an integral. Here, sigma r corresponds to the Raman susceptibility, Kr, okay, which is a function of omega. And so sigma r here is a function of time. So we obtain this function by taking the inverse Fourier transform of the frequency dependence of the Raman susceptibility. Here you have the evolution of the Raman susceptibility as a function of the frequency. A solid line gives the imaginary part, and the dashed line here gives the real part. So the Raman gain is proportional to the imaginary part of the Raman susceptibility. So the Raman gain is these curves. So you can see that we have a maximum at a frequency which is exactly 13.2 terahertz. And we have a full width at half maximum, which is about 3.5 terahertz. So that means with the Raman effect, it's possible to build a Raman amplifier with a wide bandwidth, and also it's possible to develop Raman laser, which can be tuned over a wide spectral range, typically over about 10 terahertz. So here it's an example of Raman spectrum, which has been recorded for an input power of 200 watts, with a neodymium laser generated 5 nanoseconds duration pulses at the wavelength 532 nanometers. And the fiber length here was 14 meters. It's a single mode fiber, very standard single mode fiber. And you can see that we can generate a very strong Stokes Raman line, which is shifted by 13.2 terahertz. Here, I don't show the anti-Stokes part because there is nothing to see. We cannot see the anti-Stokes Raman line. And you can see the first Stokes here has a very strong energy. The energy is proportional to the area of the line. If you compare its energy with respect to the initial pump energy, so we have a very strong transfer of energy between the pump and the first Stokes. So that means that the first Stokes is strong enough to serve as a pump and to generate its own Stokes Raman radiations. So we have a process in a cascade. So here we have a cascade of Raman Stokes, and we have exactly 4 Stokes lines, which are exactly separated by 13.2 terahertz. And if you look at the line shape, it's a nearly Lorentzian line shape, and with a width which varies from 2 terahertz up to 3.5 terahertz for the first to the first order Stokes lines. So this broadening comes from different interaction within the system. We have interaction with four-wave mixing, with cross-care effect, and so on. So that's the reason we have this broadening from the first order to the first order Stokes line. So now, how to take into account this Raman effect in the propagation equations? So we have to generalize the nonlinear Schrödinger equations. So that can be simply done by adding to the nonlinear Schrödinger equation the Raman integral. And here, rho is the fractional part of the Raman susceptibility to the total nonlinear susceptibility. So for silica fiber, rho is about 18%. So you have here 1 minus rho, which is the Kerr contribution, and a term which is proportional to rho, which is the Raman contribution. And again here, the Raman susceptibility, which depends on time, is obtained by the inverse Fourier transform of the spectral Raman susceptibility, which is given here. Okay. You take the inverse Fourier transform of this part, and you obtain the temporal response of the Raman contribution. So it's possible to expand this integral here from a standard Taylor expansion, and you have this expansion here with different coefficients, C1, C2, and C3, and these coefficients are given here. So this expansion can be useful to understand the things more physically. But if you do numerical simulation, it's not necessary to expand that. You have just to calculate the integral. It's OK. So now I will try to explain a phenomenon which is very interesting, which is called Raman-induced frequency shift. So we will consider the case of picosecond pulses, typically 1 picosecond or sub-picosecond pulses. So we can consider a transform-limited pulses. So that means the spectral width is about 1 terahertz. Okay? So it's smaller than the frequency shift of the Raman effect, which is 13 terahertz, but it's large enough to have a significant intrapulse Raman effect. So if you look at the spectrum, here I considered the case of an hyperbolic second pulse. If you look at the initial spectrum, so you have a spectrum with a width of about 1 terahertz. So it's large enough, but it's smaller than the Raman frequency detuning. So that means that we can approximate the Raman gain by a straight line. So in the Taylor expansion, we take into account only the leading term proportional to C1. So it's OK to explain the process. So in that case, we have seen that Raman gain leads to a transfer of energy from high frequencies to low frequencies. So that means that the spectrum of the pulse will move in the red direction. So we have a Raman redshift, and so we have a shifted spectrum due to the Raman contribution. It's an intrapulse Raman effect. And this effect is known as Raman-induced frequency shift. It's also known as the soliton self-frequency shift, because it's very important in the case of a soliton, because the soliton will maintain its shape and width during propagation. So this Raman-induced frequency shift is more significant in the case of solitons, but in fact it's the same effect. So when we talk about soliton self-frequency shift, it's exactly the same effect than Raman-induced frequency shift. Okay. So to be more general, for ultra-short pulses, it's also useful to retain high-order dispersion terms in the nonlinear Schrödinger equations in the expansion of the propagation constants. So previously, we have limited the expansion to the beta-2 term. But of course, if you have very short pulses, you have a very wide spectrum. So it's necessary to expand to the third order, even to the fourth order, and so on. Okay. So here, we can expand to any order, the propagation constant. It's also, of course, crucial to take into account linear losses, okay, and to take into account the Raman contribution. So the Schrödinger equation is generalized like that. It's a more general equations. And here you can see the term which is proportional to the two losses. This is a higher order dispersion terms. Here you have a term which is called tau shock. This is a shock term, or which is called also self-steepening term. And here you have the Kerr contribution and the Raman contribution proportional to the factor rho. So what is the shock term here? The shock term, or self-steepening term, so takes into account the frequency dependence of the nonlinearity. So this is a nonlinear dispersion. Okay. So in other terms, in other words, so it also results from the fact that the group velocity depends on intensity. So that means that the peak of the pulse will move slower than the wings of the pulse. So in that case, the trailing edge here becomes steeper and steeper during propagation. So the pulse look like that during propagations. So we have a very steep trailing edge here in that case. This is the effect of self-steepening, which is exactly similar to a shock effect that we can observe with acoustic waves also. So if you need to simulate the propagation of a pulse in an optical fiber, you can use these very general equations. It takes into account every process, okay, every important process, except the fact that we don't take into account here the variation of polarizations. If you want to take into account different state of polarizations, you will have two coupled equations like that. So to illustrate the effect of Raman-induced frequency shift, we have made the following experiment on numerical simulations. In the case of an hyperbolic second pulse with a duration of 190 femtoseconds, and with peak power of about 1 kilowatt, and these pulses are injected into a microstructure fiber with a very large nonlinearity, gamma equal 80 per watt per kilometer, and with the following dispersion curve. Okay. So what is a microstructure fiber? It's a fiber in which in the cladding you have holes. So it's very interesting to manage the dispersion on nonlinearity. So here we can look at the spectral and temporal evolution of the pulses during propagations. So the fiber length here was only 1.2 meters. Okay. And we can see very different interesting things. If you look at the first stage of propagations, during the first centimeters of propagations, so cell phase modulation will dominate, and we'll have also, thanks to the contribution of dispersion, you will have a solitonic compression. So cell phase modulation on solitonic compression. So, and when at a distance, at a few centimeters, when spectral broadening is maximum, so approximately given by the ratio between the dispersion length and the number n that we have defined previously, and at this propagation distance, so the higher order solitons undergoes a fission process due to the perturbations induced by third higher order dispersion and Raman effect. So during this fission of soliton, the pulse splits into n fundamental solitons, where n here is the integer smaller than the closest to the value of n. In our experiments, n was equal to 3.4, so that means here we will have 3 pulses generating through the solitonic fission. And it's possible to define the width on the peak of these different fundamental solitons. It's a relatively complex exercise, but it's possible to do that with the inverse scattering method, and we obtain the pulse duration and peak power of the different fundamental solitons which are generating through this solitonic fission. And here k varies from 1 to n. No, so here we have k equal 1, 2, and 3. So we can see that we have exactly 3 solitons here, 1, 2, 3, and you can see also in the temporal domain. Okay. And so these solitons are generated one by one. They are not generated simultaneously. And the first soliton, which is generated, is the one with the lowest duration and highest peak power. So this is the one which will undergo the most efficient soliton self-frequency shift. So this is this one. This is one which is ejected first. So it will undergo a large soliton frequency shift. Okay. And the 2 others have a larger duration and smaller peak power, so they will not undergo a strong Raman frequency shift, just a small frequency shift. So as you can see, these 3 fundamental solitons have different frequencies, and because of third order dispersion, they will move at different velocities. So that's exactly what we see on this figure, which shows the temporal evolutions. So the 3 solitons move at different speeds. And the solitons, which is injected first, will move at the faster velocity. And the 2 others remain relatively close. Okay. So now it's a similar experiment, but we change the fiber. The initial condition for the pulse are exactly the same. So we take, again, femtosecond pulses with the same input power. But as you can see, if you look at the dispersion curve, so you have 2 zero wavelength dispersion point, one here, second here, at more than 2 microns. So this zero dispersion point does not play any role in the process here. But if you change the optical fiber in such a way that the second zero dispersion wavelength is here close to 1.3 microns, so it will play an important role in the process of pulse propagations. Indeed, and you can see as the first solitons undergoes this Raman shift, so when it will approach the second zero dispersion point, so it cannot go into the normal dispersion regime. Here we are in the anomalous dispersion regime, and on the right you have the normal dispersion regime. So we know that solitons cannot exist for normal dispersion. So the soliton will be stopped when it will approach the second dispersion, the second zero dispersion wavelength. And when he will stop, he will transfer energy, a part of his energy, to a dispersive wave. And at which wavelength? At a wavelength at which the dispersive wavelengths, the dispersive waves propagate with the same velocity that the shifted soliton. So it's to increase the process, the efficiency of the process of energy conversion between the soliton and the dispersive wave. So this dispersive wave is also known as the Cherenkov radiation. So these Cherenkov radiations will move at the same velocity than the shifted soliton. So it's exactly that you can see on this figure. Here you have the shifted soliton, and in red the dispersive wave, and you can see that they move together at about the same velocity. This is due to this second zero dispersion wavelength that you have with this particular fiber. So I think that we have now a different process, and we can understand with this process phase modulation, dispersion for wave mixing, Pierre effect, modulational instabilities, solitons, soliton fission, higher order solitons, and so on. We can understand relatively complex things. And we will see the case, a particular case of supercontinuum generation. But before that, we will take a look at the link that we have between hydrodynamics and nonlinear optics. So it's well known that there is a strong link between hydrodynamics and optics. Indeed, in each case, solitons can exist, and also the process of modulational instability. In the case of water waves, the modulational instability is known as the Benjamin-Fair instability, but it's the same. Okay. And the solitons were first observed in the case of hydrodynamics a long time ago, in 1834 by John Scott Russell. And it's interesting to know that the second observation of the hydrodynamic soliton was observed in Dijon by Henri Bazin and Henri Darcy nearly 30 years after. So in Dijon, we have many specialties, mustard, but we have also the specialty about solitons. And modulational instability, which is known as the Benjamin-Fair instability, was observed about at the same time in the case of hydrodynamic waves and in the case of optical waves. In each case, we have a simple model which is well adapted to both fields. So this is the self-focusing nonlinear Schrödinger equations. So in the case of water waves, the nonlinear Schrödinger equation is valid only if you have deep water. It's not valid for shallow water. Okay. In the case of shallow water, the equations which derives from the earlier equation is the Korteweg-de Vries equation, which is known as KdV equations. So you will have the NLS equations for deep water, which is the case in the ocean. If you look at waves in the ocean at a large distance with respect to the beach, you are in the case of the nonlinear Schrödinger equation. So we'll take a look at the first-order solutions of the nonlinear Schrödinger equations. We have seen one example. This is the simple solitons, the scalar solitons, which is localized in time. But there are other families of first-order solutions of the NLS equations, which correspond to solution on finite background, which we call SFB. Okay. And in particular, there are two families of SFB solitons, a family which is known as Akhmediev breathers, which are localized in space, and the second family of SFB solitons, which are the Kuznetsov-Mas solitons, or the KM solitons, which are localized in time. And here you can see on this diagram the interrelation between the different solutions. They correspond to only first-order solutions to the NLS equation, but we have also second-order and so on solutions which are more complex. So if you take a look at this diagram, you can see, for example, that the peregrine soliton, which is a particular case of a soliton on finite background, is a limit case of a family of Kuznetsov-Mas soliton, but also a particular case, a limit case, of a family of Akhmediev breather soliton. The KM soliton are localized in time. The Akhmediev breathers are localized in space. So that means that the peregrine soliton will be localized both in time and space. You have a strong localization in the case of the peregrine solitons. For example, here you have the solution which correspond to a plane wave. Here you have stationary periodic solutions which correspond to cnoidal waves. And inside the triangle, you have biperiodic Jacobi's elliptic functions. So it's possible to calculate to have all the first-order solutions. So let's take a look in more detail to the case of the Akhmediev breathers solitons. So they have been derived by Akhmediev 30 years ago. And the solutions of these Akhmediev breathers are given here. So they use hyperbolic function, cosine hyperbolic, sine hyperbolic functions. And they depend on one parameter, which is a parameter A here, which is a modulation parameter. And here B is proportional to the gain, and to the modulational instability gain, and omega is the frequency of the perturbation. So all these solutions here are related to the process of induced modulational instability. So we understand here that modulational instability is a very important process, very general process. Each solution here can be induced, generated by the process of induced modulational instability. So it's exactly the case of the Akhmediev breather. To generate an Akhmediev breather, so you induce a small perturbation here on a finite background. And we can see here you have time, here you have space. And you can see that during propagation, these small perturbations will generate a pulse. And so you have a strong focus of energy. And then this energy disperses. So the pulse bursts only once. So it's localized in space. So it's really related to the rogue waves that we can observe in the oceans. So we have a strong waves which appear suddenly and disappeared without a trace sometimes. Okay, so these breather solutions correspond to the case where the parameter A is less than 0.5. So here, this is the particular case of the peregrine soliton, which is the limit case of the Akhmediev breathers. So the peregrine soliton is obtained when the value of the parameter A is equal to 1/2. But you can see that when you have A equal 1/2, the MI gain is very small. It's close to 0. Okay. So that's the reason why it's difficult, of course, to observe the peregrine soliton, because it corresponds to a 0 gain. Okay. So to observe the peregrine soliton, we have to approach this value of, we have to have a very small initial modulation frequency. Okay. So that's the reason that it's difficult to observe the peregrine soliton. So it was predicted in 1983 by Peregrine and was observed for the first time by Bertrand Kibler and collaborators in my group in 5 years ago about. And now it's considered as a prototype for the ocean rock waves. And you can see here what can happen if a ship meet such rock waves. So it's very important to understand, of course, the formation of this rock wave, and the idea is to try to predict their formation. So it's a big challenge, okay, to try to predict the formation of this rock wave. But the first step is done. Now we know that how they are formed. Okay? They are generated. They are generated from the induced modulational instability. So here on this figure, we can see the different waves that we can obtain for different values of the parameter A. So we are in the case of soliton on finite background. And when A is less than 0.5, so you have the Akhmediev breathers, which are localized in space and periodic in time. In that case, the parameters omega and B are real functions. And if A is larger than 1/2, so you have the Kuznetsov-Ma solutions, which are localized in time but periodic in space. So that's the opposite. So in the particular case where A is equal to 1/2, okay, so you have the peregrine soliton, which is localized both in space and in time. So we have also observed the Kuznetsov-Ma solitons in 3 years ago. It was predicted in 1977. So the idea is to induce modulational instability with very particular initial conditions. So in the case of optical fibers, it's very, it's not simple, but we can do experiments which are very stable, and we can adjust the initial conditions to have exactly the right initial conditions necessary to generate the peregrine or the KM solitons. So optical fibers are very useful to observe very general phenomena which can be observed in different systems. It's also possible to use optical fibers to observe ondular bores. So what are ondular bores? We have two examples here in the nature. So one is observed in a river in Canada, and the other ondular bores corresponds to the morning glory cloud, which can be observed in Australia. And the idea was to observe for the first time this kind of ondular bores in optics. So for that, we have used the process of modulational instability coupled with four-wave mixings. So we can generate here, this is what we have observed in the case of optical fibers. So with particular initial conditions, you will have four-wave mixing and modulational instability, which take place simultaneously, and we generate shock waves at this point. And after the shock waves, you will have generation of these ondular bores, which are very similar to the ondular bores that we can observe in nature in hydrodynamic waves or in the case of clouds. If you are interested to know more details, you can have a look to this paper. So now I will talk about the generation of supercontinuum in optical fibers. So there is what is a supercontinuum? There is no exact definition what is a supercontinuum. It's a light, an intense light with a very broad spectrum. But what means intense, what means very broad, it's not very clear. That depends of the type of experiments that you do. That depends on the applications that you are interested in. But what is sure, it's like it's as broad as a lamp. It's bright as a laser. So we can talk about a laser rainbow. So it's very simple to generate experimentally. You have just to take a laser to inject the pulses into an optical fiber and at a certain power levels, and depending on the type of optical fiber that you have, you can observe a very broad spectrum at the fiber output. So the experiment is not difficult to do, to perform. But the explanation is more difficult. But we have all the ingredients to understand the formation of a supercontinuum. And this supercontinuum can be understood depending on the 4 conditions. That depends on the sign of the dispersion. That depends if you have normal or anomalous dispersion. And that depends on the pulse durations. So we have essentially 4 supercontinuum regimes. So if you take into account the case of short pulses, for example, less than 1 picosecond, and if you use an optical fiber in a normal dispersion regime. So in that case, there are 2 processes which play a significant role. This is the self-phase modulation and the wave-breaking effect. I will talk about the wave-breaking effect a little bit later. And if you, again, for the same short pulses, if you are in the anomalous dispersion regime, so this is the regime of solitons. So the dynamics is essentially governed by solitons. But as we have seen previously, we will have the generation of dispersive waves, Cherenkov radiation. You will have the effect of soliton self-frequency shift. So these 3 main physical processes will be very important in that case. Now, if you consider the case of longer pulses, if you are in the normal dispersion regime, the effect which is the most significant is the Raman effect. If you are in the anomalous dispersion regime, so the most important effect will be modulational instability. But as we have seen previously, modulational instability can generate solitons. Okay? So you will have also a contribution of solitons on dispersive wave Cherenkov radiations. And because we have also very long pulses, we'll have the contribution of Raman effect. And of course, if you have Raman and solitons induced by modulational instability, you will have the effect of soliton self-frequency shift. So you can see that depending on these the input conditions, the physical phenomena which play a crucial role are these phenomena that we have explained previously. So you have the main ingredients to understand the formation of a supercontinuum. So I will take 2 examples, the case of short pulses and then the case of long pulses. So here we consider the case of femtosecond pulses with a full width at half maximum of 50 femtoseconds at a wavelength of nearly 300 nanometers with a pulse energy of 0.5 nanojoule. And we inject these pulses into a photonic crystal fiber with a length of about 15 centimeters. So if we calculate the n number, so the soliton number, we will find that n is about 9. So we are in the situation of higher order solitons. So if you look at the spectral and temporal evolutions of the pulses during propagations, so we can see that we have a strong spectral broadening, which at the end of propagation covers a wide spectral range from 600 nanometers to about 1,200 nanometers. It's more than 1 octave. Okay. So when you see that this kind of spectrum, you say, how to explain that? It seems very complex. But if you look in the time domain, so it's more simple to understand. So you can see that at the beginning of the propagation, so the phase modulation and soliton compression act together, and you have a compression of the pulse. Okay? And at a certain distance, we will have a soliton fission, okay, and generation of a dispersive wave, of shrink-off radiation that you can see here. And then you have the effect of soliton self-frequency shift. So if you take into account this effect, you reproduce exactly this spectrum. So this is the same explanation, but with the two color maps. So here you can see the dispersive wave, which move about at the same velocity than the shifted soliton. And you can see here the Raman shift and the dispersive wave in the spectrum. So now, let's consider the case of a long pulse. So a pulse in the nanosecond regime, so typically 1 nanosecond. So at a wavelength of about 1,000 nanometers, this is a neodymium laser. And we consider here the case of PCF, photonic crystal fiber, with a length of 4 meters. And here we look at the spectrum for different power injected into the fiber. Okay? And we fix, in that case, we fix the propagation distance. So it's 4 meters. So at relatively low power, you can see several sidebands, which corresponds to modulational instability sidebands. So that means we are in the anomalous dispersion regime. If you increase, you have a cascade of modulational instability sidebands, like a cascade of Raman and Stokes. This is the same effect. Okay? Now, if you increase the power up to 43 watts, you have again the modulational instability process, of course, but you can see the onset of the first Raman-Stokes radiation. And if you increase again the power up to about 100 watts, you can see that Raman cascade, the Raman cascade of Stokes radiation is the most important effect. So we can understand in that case the formation of the supercontinuum in the case of long pulses. Okay, so now we'll take a look to very particular pulses, which are called similaritons. So similaritons are different of solitons. They are not the same. Up to now, we have considered propagation of pulses in a passive fiber, in a passive system. We don't have any gain. Now, what happens if you consider propagation through an amplifier, for example? So we have a gain now, so that will change the dynamics of the system. If you are in the anomalous dispersion regime, this is the regime of solitons. So if you add gains in the nonlinear Schrödinger equation, in that case, you will generate higher order solitons. You will have soliton fission, so on, so on. So the dynamics will be very similar to the ones that we have in a passive systems. So the gain will just increase the process, but the process will be about the same. Now it's very different if we are in the normal dispersion regime. In the normal dispersion regime, usually in an optical amplifier, you can have the effect of wave breaking. So as the name said, that we have a generation of oscillation in the pulses, which are called a wave breaking effect. So the goal is to know how to amplify short pulses. You know, it's a difficult task because when you have very short pulses, picosecond or femtosecond pulses, if you send these pulses into an amplifier, you will have a strong contribution of the nonlinear effect. So you will have a strong distortion of the pulses. So usually the idea is to broaden the pulses and then amplify these broadened pulses and then to compress again the pulses. So this is a technique of CPA that you probably know. But it's, you have 3 stages: broadening, pulse broadening, amplification, pulse compression. Okay? So the idea here is to avoid to combine the 2 first stages into a single one. So the idea is to use an amplifier in normal dispersions. So in that case, we will see that we obtain very particular solutions. We are asymptotic solutions, and which are parabolic pulses with a linear chirp. And these pulses propagate self-similarly. So that's the reason we call these pulses similaritons. And if you can observe parabolic pulses in an optical amplifier, that means that you can generate this type of pulses in a laser. And the first similariton laser was developed a few years ago in the group of Frank Wise in USA. So now, to explain these particular pulses in more detail, so we consider again the nonlinear Schrödinger equation, and we add a gain term. And here, that you can see here, and here, just to simplify the things again, to have analytical solutions, we consider that the gain is constant in frequency, so we neglect the spectral dependence of the gain. So it's an approximation, of course. And we also assume that the gain is constant during propagation. So that means that we neglect the pump depletion. Okay? But you will see that these approximations are very interesting because they lead to the most important physical characteristic of the pulses. So it has been shown that this equation here, the NLS equations with the gain term, admit asymptotic solutions. So in the limit of the propagation distance tends to infinity, which are characterized by a parabolic intensity profile and with a positive linear chirp. And they have parabolic shapes, so that means they have a compact support. And you can see these asymptotic solutions are given by this function here. So you see here the parabolic function, okay, and the support, the compact support here. So the pulses only exist for a time between minus Tp and plus Tp. Okay? So Tp is proportional to the pulse width of the parabolic pulse. And here, phi p is just a phase offset, which depends on the propagation distance, but it does not depend on time. So it's not a very interesting part. But if you look at the phase, temporal phase here, you can see that we have a quadratic term. So that means that we have a linear chirp. Okay. And it's possible to have the expression of these different terms. So we can express the width of the parabolic pulse. Its proportion is given by this expression here. You have an exponential evolution of the width as a function of the propagation distance, depending on the gain, G. Okay. And here, the other parameters which play a role are the amplifier parameters, gain, G, nonlinearity, gamma, dispersion, beta 2. Okay. And you have a parameter here, A0. So A0, again, depends on gamma, beta 2, and G, but it depends on the initial energy of the pulse that you send into your amplifier. Okay. If you look at the peak of the pulses, you can see that the peak power is also proportional to this constant A0. It's proportional to A0 square. And it evolves exponentially with exactly the same function than the width of the pulse. Here we have exponential 2gz over 3, and here you have exponential gz over 3. So you have an exponential amplification of the pulse, similarly to an exponential increase of its width. So that means that the pulse propagates self-similarly. So we have a self-similarity process here. So that's the reason why we call these pulses similaritons. If you look at the value now of the linear chirp, so Cp, so it's proportional to the gain, G, and proportional to the inversely proportional to the dispersion. But it does not depend on the initial energy. Okay. So it's a constant, this chirp, which only depends on the gain and the dispersion of the amplifier. So what is very interesting here also is that the initial pulse shape does not play any role. What is important is only the pulse energy. So it's not important to have a special shape to generate these similaritons. You can generate similaritons with Gaussian pulses, with secant hyperbolic pulses, with every type of shapes. So the only significant parameter is the pulse energy. So that's very interesting. So it's possible to observe these parabolic pulses in the case of a Raman amplifier. So in that case, we have considered an optical fiber with these parameters here, beta 2, beta 3, gamma. And the pump wavelength was in the telecommunication band, in the C band, so around 1,550 nanometers. So we are here in the normal dispersion regime. Beta 2 is positive. Okay. So, of course, to have an amplifier, you have to put energy in your system. And in the case of a Raman amplifier, so we use a Raman pump, which is a CW pump here, at a wavelength of 1,555 nanometers. So which is shifted by about 100 nanometers with respect to the wavelength of the pulses that you try to amplify. So that corresponds to exactly to the Raman shift 13.2 terahertz. So in these wavelength domains that correspond to about 100 nanometers. And the pump, of course, is shifted in the anti-Stokes sides to amplify the Stokes radiation. Okay. So at the fiber output, here the fiber length was about 5 kilometers. And at the fiber output, so we can separate the residual pump and characterize the pulses. And in that case, we have used a particular system which use second harmonic generation, which are frequency resolved. So this system is called FROG, for frequency resolved optical gating. So I don't have time to go into the details. So it's just a spectrally resolved autocorrelation. Okay. And from this spectrally resolved autocorrelation, so you get a FROG trace, and with some algorithms, it's possible to retrieve the phase and the amplitude of the waves. So it's very interesting because you have information on the chirp. It's not direct measurement. Okay. So this is the results that we have obtained. So here, this is the numerical simulation, and this is the experimental result on the right. And here you can see the results in more detail. So here you have the intensity profile on the chirp that we have retrieved from the FROG trace. Okay. And here it's exactly the same in log scale. Here it's in linear scale, and it's the same in log scale. So the experimental data are given by the solid line. If you look at the chirp, you can see that we have a linear chirp, positive linear chop. And if you look at the profile, here the cycles are a parabolic fit. And you can see that you have a good agreement between the parabolic fit and the experimental data. And you can see this good agreement in log scales. And if you compare this with a fit with a Gaussian or an hyperbolic second function, you can see a very strong difference in the wings of the pulse. So that means we have really generated a compact pulses, parabolic pulses. So what is very interesting here for this type of pulses is that, of course, the pulse amplifies during propagations and its width increases. So you can have a lot of energy within the pulse. So we have amplified the pulse, and you have a linear chirp which can be compensated very simply, and to obtain ultra-short, intense pulses. So the idea is, the most important part is this linear chirp. Okay, so the last example that I will consider is the generation of frequency combs. We have already seen an example. By using induced modulational instability, it's possible to generate frequency comb. But of course, the generation of frequency comb is not so difficult. You have just to use a mod-lock laser. Okay. But you have to stabilize this mod-lock laser, of course, because in a frequency comb, there are two important parameters. This is, of course, the frequency separation between two frequency combs, which depends on the laser length cavity. Okay? So you have to control the length of the cavity. But there is also, because in the amplifier, you have dispersion on Okay? So that means that the carrier waves will not move at the same velocity than the pulses which move with the group velocity. Okay? So you have a difference between the phase and the group velocity, so that needs a frequency offset in your frequency comb. So you have two parameters to control, the frequency offset and the cavity length of your laser. But it's something that can be done relatively easily. So to generate a frequency comb, it's relatively simple. But it's more difficult to generate two frequency combs which are mutually coherent together. Okay. So in my group, we have proposed an idea to generate two mutually frequency combs without any locking system, complex locking systems. So the idea is very simple, and you will see we'll use some effects that we have explained in optical fibers, phase modulation, wave breaking, and so on. And so the idea is to use a single diode laser, which generate a continuous wave, and we can amplify this wave if necessary. And then this wave is split into two equal intensity parts with a fiber coupler, and these two beams are then intensity modulated by two electrical intensity modulators, which are driven by two electrical pulse generators, driven by two electrical clocks, and set at different frequencies, slight different frequencies, 300 megahertz and 300.1 megahertz. So in that way, we can generate a train of pulses, which are relatively long pulses of a few tenths of picoseconds, because we are limited by the speed of electronics, of course. We are limited by the speed of the modulators. So we have characterized these pulses. We have generated nearly square pulses with a full width at half maximum of about 50 picoseconds. And if you look at the spectrum, of course, we have a sinc shape, which is the Fourier transform of a square. Okay, so it's not surprising. And you have a pulse bandwidth here of about 0.2 nanometer. So it's not very large. So we cannot say that we have a frequency comb. So the idea is now is to broaden spectrally broaden this train of pulses to generate frequency combs. So you have an example here of a frequency comb after a spectral broadening. So we can see here we have about 1,000 frequency combs. So how to broaden these pulse trains? So the idea is to use an amplifier in a normal dispersion regime. So for that, we amplify the pulses, and we control their polarizations, and we send these pulses into a dispersion compensated fiber, DCF, with a strong normal dispersion. So we are in the normal dispersion regime. And pulse broadening in the normal dispersion regime is mainly determined by optical wave breaking. So what is exactly optical wave breaking? So I will try to explain this very simply. So in the first stage of propagation, we have a strong nonlinearity. So safe phase modulation will be the dominant effect. So you have a chirp like that, which is generated by safe phase modulation. But because of normal dispersion, the leading edge of the pulse will travel faster than the trailing edge. And that generates a pulse broadening and the appearance of a plateau. You have nearly a square pulses, which is generated by this process. And if you look in the spectral domain, here this is the evolution of the initial pulse as the function of the propagation distance. Distance increase from back to front here. So as you can see that the spectrum broadens and becomes relatively flat at the fiber output. So it's very interesting. So we have not a super continuum because it's only 3 nanometers, but we have a large spectrum and a very flat spectrum. So it's very interesting for application. If you do the same things in anomalous dispersion regime, so with safe phase modulation, you know that the spectrum has very strong oscillations. So it's less interesting for applications. And the second point, which is very important, is that when you are in the anomalous dispersion regime, this is the regime of solitons, but also the regime of modulational instabilities. So you will have instabilities, solitons. So it's a regime where the spectrum is not really coherent. But for normal dispersion, you can get a spectrum which is relatively coherent. We'll check that just later. So this is the results of the experiment. So we have used a DCF here with a dispersion coefficient D, which is equal to minus 94 picoseconds per nanometer per kilometer. So we are in the normal dispersion regime. The fiber length is 1.38 kilometers. And you can see here the evolution of the spectrum for different input power from 3 dBm to 24 dBm. Just remember that 20 dBm is 100 milliwatts. Okay. It's a log scale. 0 dBm is 1 milliwatt. Okay. And you can see that for a certain power, so you obtain a very flat spectrum, and contrary to what you could obtain in the regime of safe phase modulation. And you have a plateau here, and with a very small intensity fluctuation. So it's very interesting. And the bandwidth here is about 3 nanometers for 24 dBm. But if you increase the power, it's possible to have a spectrum of about 10 nanometers. So 10 nanometers becomes interesting for application. So there is a very important point. So how to broaden the two frequency comps, which were initially mutually coherent because they were generated from the same single laser, or the same laser. So they have a mutual coherence, of course. But during amplification in the optical fiber, this mutual coherence can be destroyed. Okay. So to avoid this, the idea is to use the same fiber to broaden the two frequency comps. For example, with a fiber with a length of about 1 kilometer, you know that an optical fiber is a very sensitive sensor. And if you calculate the variation of temperature, if you take into account the variation of temperature, you will find that a variation of temperature of 1,000 of Kelvin will induce a shift of 2 pi, a phase shift of 2 pi. So it's nearly impossible to control this temperature and to use different optical fibers. So the idea is to use the same optical fiber to broaden the two frequency comps, and the two frequency comps so counter-propagate into the fiber. We use here two circulators, and at the fiber ends of at each fiber ends we put a circulator, and after the circulator we combine again the two frequency comps. And with this system, it's possible to maintain the mutual coherence between the two comps. And to check that, we have looked at an interference line between the two comps, and we use a radio frequency spectrometer. And we have compared the line width of the interference line between the two comps before and after spectral broadening, and we can see that we observe exactly the same width, 2.5 Hertz, which corresponds to the full width at half maximum. This is for the 3 megahertz line, but we obtain exactly the same results for each comb line. Okay. So with this system, we have generated two mutually frequency combs. So it's interesting for different applications. For example, it's interesting to do dual comb spectroscopy. So what is dual comb spectroscopy? It's similar to the Michelson Fourier transform spectroscopy, but instead of using a Michelson interferometer, here you use two frequency combs at slightly different frequency repetition rates. For example, 3 megahertz and 3.1 megahertz. So we have a frequency shift of about 100 kilohertz between the two frequency combs. And these two frequency combs are superposed in the sample, for example, in a gas sample. And they will beat together, of course. They have slightly different frequency repetition rates. So they generate a beat in the radio frequency domain. So in this radio frequency domain, so you can observe the absorption of the medium if you look at the absorption. But you can do also nonlinear spectroscopy. We can do the same with Raman spectroscopy, for example. And so it's, of course, it's very easy to detect, to record the radio frequency spectrum instead of recording the optical frequency combs. So it's like an heterodyne detection. It's exactly what you do when you use your radio. Okay. So just take a look at an example. So we applied this dual comb spectroscopy to study the absorption of carbon dioxide, or HCN. The idea here was just to check the performance of the system. It's not to study the absorption of CO2. Absorption of CO2 is well known, of course. And here you can see the interferogram, so that you observe. This is the interference between the two combs. Okay. And the period of the interferogram depends on the frequency detuning that you have between the two combs. Here it's typically 10 microseconds. And if you take the Fourier transform of this interferogram, so you directly get the absorption spectrum. Here you can see 3 absorption lines. And if you fit this data with a superposition of Lorentzian profiles or Voigt profiles, you can obtain a relatively good agreement. Here we have intensity fluctuations because in that case we have used an hollow core optical fiber to increase the absorption length, and we have a contribution of the surface mode inside the fiber, which leads to an interference effect and which leads to these small fluctuations. But if you use a multipass cell, for example, it's the case that we have for HCN. HCN has been obtained here in the case of a multipass cell, not a hollow core fiber. You can see that we have a very clean fit between the experimental data and a Voigt profile. So just an application of wave breaking and supercontinuum generation and so on. So in conclusion, so we have seen that optical fibers can be used with relatively low intensity level, a few gigawatt per centimeter square, but allow us to obtain very long interaction lengths. So we can study very small effect with optical fibers. And besides their well-known application to high-speed telecommunications, optical fiber constitute an ideal photonic platform to study nonlinear phenomena with high accuracy, because we have high stability with optical fibers. And so you can integrate over a long time and to see very small effect with high accuracy. And under certain regimes, the behavior of light in optical fibers mimics the dynamics of classical fluids, and in particular hydrodynamical phenomena. So we have seen that it's possible to observe the peregrine soliton or the Kuznetsov-Mah soliton or ondular bores, and the peregrine soliton is now a prototype of the ocean rock waves. So this is the observation in optics which has which has stimulated experiments in hydrodynamics. After our first observation of the optical peregrine soliton, the peregrine soliton has been observed in a water tank. So we will see just in a few minutes some movies, but before that, so you will find in the PDF of this presentation a few bibliographies. So one important book is a book of Gowin Agrawal about nonlinear fiber optics. So you will find many details in this book. So it was impossible for me to summarize this book in a few hours. Okay, it's a very interesting book. But there is also a very interesting book from a colleague in Dijon who is now retired, Michel Moisnet, a book which is called Waves Called Solitons. It's more general. It's not focused only in optics, but in mechanics, in hydrodynamics, in many different systems. And you have also, see, three chapters that I have written with one colleague in the Encyclopedia of Modern Optics, which give more details. And also maybe an interesting paper about the non-linear polarization effect and about the polarization attraction effect that we can see in optical fibers. And it's related also to modulational instability. Just a pedagogical note that we have published with John Dudley about 10 years ago about the cancellation of dispersive and nonlinear phase shift to explain the concept of soliton, because even in the best textbooks, the solitons are usually explained with the case of a Gaussian. But with a Gaussian, we can have a soliton. So, and different other papers about the peregrine solitons, the Kuznetsov-Mah solitons, and the observation on the ondular bores. So now we will see just a movie to conclude. So in Dijon, we have a water tank, a water channel, which has a length of about 18 meters, a width of about 50 centimeters, and a depth of about 60 centimeters. And we have a log systems to generate waves. In this case, we will put a high level of water in the log system. So we will generate a large amplitude waves. So what we will see, we'll see the effect of wave breaking, which is similar to the wave breaking in optics, or similar to the wave breaking that you can see on the beach. Okay? So we have a large amplitude wave. So you can see the effect of wave breaking. Okay. So now we'll try to generate the solitons. So for that, we have to have an exact balance between the dispersion effect and the nonlinearity. In this case, we are in the case of shallow water. So the equation is not the nonlinear Schrödinger equation. It's KdV. And we don't have a carrier wave. We have just the envelope wave. To have the Schrödinger equation, you have to have a carrier wave. Okay? So in that case, you should have a wave maker, okay, to generate a carrier wave. So but it's similar. Okay? We have different type of solitons. And so for a certain level of water in the log system, we'll have a compensation of between dispersion and nonlinearity. So we generate solitons. I see trees of green. So we generate a soliton. It will reflect at the other end of the channel. For me and you, and I think to myself, what a wonderful world. So the following movie is to generate a collision between two solitons. So we generate a solitons, and when it will reflect at the other end of the tank, we launch another solitons. So they will collide in the middle of the channel. Okay. The collision of solitons. This is the first soliton. Okay. We launch the second soliton. Okay, be careful. Oops. One more time. Okay. Thank you very much for your attention.